Hello, my name is Johan Kraft. I'm CEO and founder of Percepio, a Swedish company focusing on trace visualization for embedded software development. Today I'm going to talk about Percepio+Trace for Atmel Studio, an integrated part of Atmel Studio 6.2. Tracing means that you record and visualize the runtime behavior of a software application. The recording can be implemented either using hardware features such as those present in Cortex-M, SAM3 and SAM4 MCUs. Another approach to tracing is to use a pure software solution, like we do in other tracealizer products. So, tracing, when is that useful then? Well, if you have complex problems where there is a certain time from the actual bug until the symptoms appear, you want to know what was going on in the system leading up to this error. Another side of tracing is to study timing issues and performance in general. The source code alone does not give you the full picture of the system since there's no timing information, but if you record what's going on in runtime, you see exactly how long time things take to execute and when things occur and in what order, etc. Percepio+Trace is found in the Debug menu here and also in a toolbar up here. The toolbar is not shown by default, but it can be enabled from the View menu. The first thing you will need to look into is the Trace Settings dialog found if you click on the P button for Percepio. Here you need to specify the clock frequency of the chip, and it can be good to put a breakpoint in the main function after that the clock has been initialized, when you know that the system is running at this frequency, and use this breakpoint as the starting point of the tracing. Here's a glimpse of the control flow trace, showing tasks, FreeRTOS in this case, and interrupts. This can be generated without any software instrumentation, using the integrated hardware trace features in SAM3 and SAM4 MCUs. Data trace works in a similar way. It records write operations to a particular memory address. Each data point here represents a particular write to the address, and if you click on these data points, you see where in the code it occurred. Percepio+Trace also contains profiling functions. In the upper right, you have the PC sampling timeline that gives you functions that use most processor time, over time, so to say. Each row here represents a couple of seconds of execution. Below that, you have an overview showing the total processor time of different functions. And if you click on any of these, you see the source code in the left with graphical annotations that reveal how many samples that have hit the different lines in the source code. In this case, the first annotation, the first line here says 1.6% in the left side margin, and that means that 1.6% of the samples in this function hit that particular line. Percepio+Trace also allows for using debug prints, a serial wire output. This is similar to a classic printf, but in the serial port, the prints are channeled through the debugger and show up in Atmel Studio in the output window under the Percepio+Trace label. For reference, here's the code you need to generate a serial wire output prints. To illustrate a bit more how you can use these functions, we have prepared a demonstration project. It's a basic SAM3 development board with a classic SAMICE debugger. We have a FreeRTOS project that has 3 issues that we're going to look into. Data corruption problem, task scheduling issue, and there's also a performance issue that we're going to analyze. So let's switch over to Atmel Studio.
Okay, let's begin by checking the settings. The clock frequency is set to 64 MHz, which is the maximum frequency of the SAM3 MCU. We want to see the application output, data trace and RTOS events, FreeRTOS in this case. A breakpoint has been set in the main routine after the hardware initialization, so we know that the clock frequency is actually 64 MHz as specified in the settings. So let's run to this point. And now we enable the tracing. And let's begin by inspecting the execution of the 2 tasks using the control flow trace. After a while, the control task takes over entirely and uses all the processor time. Why is that? When halting, we see that the control task has reached an error state due to this state variable having an illegal value. We can also see an error message printed in the output window and in the control flow trace. The variable appdata.taskState should only be assigned at these 4 locations, but there is something else obviously corrupting it since the value is 57. So let's use the data trace to see all updates of this variable. And there it is. When clicking on this data point, we see the location where the write occurred inside the read input function. This seems like a buffer overflow because it's assigned through a pointer here. And when looking closer, we see that this counter is not updated. So let's fix this bug by adding a ++. Now the system seems to be stable. Another issue is in the DAC task. This is supposed to execute periodically and generate a signal similar to a sine wave. Let's plot this signal. And when zooming in a bit, you see that the output is sometimes delayed, causing anomalies in the signal. It seems that the control task is preventing the DAC task from running. This is due to scheduling priorities. We see that the priority of the DAC task is 3 and the priority of the control task is 4. In FreeRTOS, a higher priority value means a more important task, so control is regarded as being the more important task here. And ADC is therefore not allowed to preempt the control task. This is not the intended design, so let's swap the priorities. There, now you can see that the DAC task runs periodically and that the signal is smooth and similar to a sine wave. Another thing you may have noted from the control flow trace is that the control task sometimes uses a lot of processor time. Is this necessary and what is it used for? Let's enable profiling by selecting PC sampling. Now we can see what functions that are using most of the processor time. The 2 top ones are FreeRTOS functions that runs in the background when no other task is active, but this function calculate is a part of our demo application. This loop here is supposed to refine a numerical approximation and is iterated 1000 times. Let's see what happens if we should reduce this to 100. As you can see, the relative amount of processor time used by this function has now dropped from about 2% to about 0.2%, a factor of 10 as expected. This would allow this task to run at a much higher rate. All these features and several others are now available in Atmel Studio 6.2, which can be downloaded from Atmel free of charge. Thanks for listening and have a nice day.